Got you 1 second. All right. Does nothing work here ever? This is crazy. Okay, am I on mic now? Can you hear me? Excellent. So let's turn the lights down. Can you see in the back? You okay? Excellent. So this is like the second class where the mics have been failing. It's really bizarre. And YouTube has been screwing up strangely today as well. So I've been bumped off the system twice. So if you're live watching and there's one viewer right now, good luck. We'll see. We'll see if this works. So hey, if you want to be a mentor, that's great. Also, do you know what the Buddy program is? It's this thing that I used to run, that I still run, sort of. But now Dr. Galati runs it. It's a program where we put first-year HSS students in touch with upper-year students, not for academic mentoring support, but for just hanging out. So it's an idea of creating some sort of emotional social support system. If you're interested, go to our website and sign up. Our first meeting is coming up soon. The website is hssbuddies-amis.ca. Okay, so please do so. So, today we are continuing our lovely journey into frequency analysis. The hard stuff has the fun stuff, the fun sort of high school review stuff. And by the way, the hard stuff will never start. This isn't hard. It's kind of namby-pamby. And hopefully nobody went to the labs on Monday. Everyone go and was disappointed because you know it was canceled. You went? Sorry. Then you had some quality time by yourself. That's great, because Fuzzy Boys had a medical thing and he couldn't go. But we'll catch up, of course, in future lab sessions. And I'm sure the lab tech guys were just furious that the place was empty. But whatever, they get paid. Okay, what are these? What are these numbers? They're just numbers, right? And it's a misleading question. The answer is they're data. And at what point does data become information? Remember this? When does data become information? Give us some context. These could be the ages of adults in your life. It could be the height in centimeters of children. It could be a number of things, right? Now, how do you summarize these data? We've been taught to summarize them as means or things like that. The choice of how you communicate the summary of this information or these data is rife with value and assumptions. So we have to be careful what summary statistic we choose. So what we do is we impose order on these data. Let's go back for a second, look at the data again. They're not in particular order, are they? They're kind of random. And in fact, when you collect data for a study that you might do, they won't come automatically ranked. They may come wrong. Maybe these are ages of grandparents that you're interviewing at an old folks home or something, and you find out that one of them is 3.2. They can't be 3.2 years old to be a grandparent, or can they? Right? So there are going to be some issues, going to be some uncleanliness, and how you deal with that uncleanliness ultimately will define the nature of your inquiry. So the frequency distribution is a way to understand our data. It tells us the shape of the data. It tells us the outliers, anything that's extreme, maybe doesn't exist there. And it tells us something resembling the kinds of summary we want to communicate. Maybe we find that it's all clustered around one number. Like everyone in your sample is like 50 years old and a couple people are 49 or 51. Then really the average would be 50, and that's a proper way of communicating a summary. Or maybe you find that there's clusters, that maybe a bunch of people are 30 years old, a bunch of people are 40 years old, a bunch are 60 years old. That's a modality. Remember that term, multimodal? Well, that's a different kind of summary you may want to communicate. So when we look at the distribution of these numbers, we gain some insight into how to communicate them and how to analyze them. So a frequency distribution, if you remember, is just a systematic arrangement of the data, and usually we begin with a frequency count, so how many times each one occurs. So it is the first step in understanding your data, to get a feel for what it is, and that's really kind of important. We also assess how clean it is. I mentioned if you have an age of 3.2, clearly that's a case of uncleanliness. And we have methods for addressing uncleanliness in data. One of the common things to do is we do like a 10% check. If you have data of thousands and thousands of individuals, I'll go back and check 10% to make sure that they're kind of reasonable. Or if there's data entry errors, I have two people entering data and I'm not sure if they're entering correctly, we choose a percentage and we go back and we visually appraise them. Or if we have missing data, how do we deal with that? There are methods. So SPSS, you'll discover, has a way to interpolate what that value of the missing data probably is. Usually take, an average, or maybe the average of what's on either side of the missing value. All kinds of strategies. So one aspect of data cleaning involves looking at two things: outliers and wild codes. So an outlier is something beyond the normal range. So again, if this was a set of the ages of people in the old folks home, I get anything from a 45-year-old to a 95-year-old, but one person's 125. One guy's like 15 years old in the old folks home. Those are outliers. They're not in the normal range. When I say outlier, gee, what's the question you might ask me about defining outliers? If I give you a data set and I say, which are the outliers? What do you struggle with? Would you know what to do? How would you define it? Yes? What would you ask me? If I give you a set of data of ages of people and I say, find me the outliers. There it is. So define outlier. How do I define outlier? And there's actually a specific definition that we'll get to. But oftentimes we never pause to think about it. Maybe this isn't an outlier. Maybe it's part of the data I should consider. So how we define what lies beyond the normal range will affect, again, how I summarize my set. Now, wild code is something that's specific to software. And let's say I'm coding in my data, if you're female you get 1, and if you're male you get 2, and always 1s and 2s and 1s and 2s and stuff, and suddenly I get a 3. That's not someone who's uncertain about their gender, that's a wild code, that's a number that doesn't belong there. Sometimes it's a typographic error, sometimes an entry error, sometimes it's something else. Right, so one of the things we look for is there something here that not just is outside the range, but makes no sense. That's a wild code. So that's the first step, is we search for those two things. So here's an example. 3 and 7 are wild codes here. Sometimes we make a code that's seemingly wild, but it means something. 7 would be no response given, or 3 would be handwritten survey unreadable, something like that. Okay, so we have to make allowances for these extra codes that maybe fall beyond the scope of the thing that we're measuring. These are sort of operationalizable aspects of our variable. So how do you deal with missing data? You have to assess how common the missing values are. If the missing values are like majority of your data set, that's really quite problematic. Most of your data is in fact not there. I'll skip that. That's not really interesting. So very often we assume that our data is normally distributed. Do you remember what I meant by that from last class? What does normally distributed mean? It follows a certain shape. What's that shape? The bell curve. For a second I thought I said Velcro, folds a Velcro shape, a bell curve, exactly. And we often make that assumption because most things in the universe really are kind of distributed that way. Well, most things in the human characteristic universe anyway. And many of our statistical tests assume a normal distribution, so we often look for that as well. So we have to understand the nature of our data. We look at the percentages of certain characteristics, what percentage are men, what percentage have a certain ethnicity, and so forth. And when we're dealing with inferential statistics, which is what again? What's inferential statistics? As opposed to descriptive statistics. What does it mean?
You use to predict.
Exactly. Inferential statistics, we'll use our sample to make assumptions or inferences about the reference population. I know I'm being really repetitive. These are the fundamental things I want to drill through your heads to make sure you won't lose this. Okay. So the nature of the distribution in many ways determines the degree to which I can make inferences about this theoretical superpopulation. Now, in SPSS, when you get around to playing with it, if you haven't done already, the way we do frequency distribution is you click on the Analyze menu button, you go to Descriptives, and you go to Frequency, and you'll see all these things pop up. All right, so you'll see that Analyze button's there, you click on that, and a drop-down menu will appear, and you select Descriptives and Frequencies. And I hope you really play with everything. Play with all the commands and break the machine if you can. That's part of the learning process. Make SPSS give up and go, stop it, stop being mean to me. And you'll see that when you select an analysis, a pop-up window will appear. All of your variables will appear here. Remember I mentioned that in the variable view in SPSS, there'll be the name of a variable like age, sex, and so forth, and there'll also be a space for a description, and that's for your use. Age, description, this is the age of my respondent. Right. Sex, this is the sex of my respondent, whatever it might be. So SPSS, its default setting, here it lists the description, not the name of the variable. You can reset the options so it lists the name. But the reason for that is usually we've got hundreds of variables and they've all got these arcane, incomprehensible names like 814612, you know, ABZ, which means like, you know, I measured this particular thing in the serum and it meant this, and you forget because you've got 1,000 variables. So that little space, that auto description, that's very useful. So when you select a variable, you just click on it and you move it over here, and this tells us the variables that you're performing the analysis on. So for descriptive command, you just move that over here and you click on these buttons here to choose the descriptive analysis that you want. So here you just want the standard deviation, skewness, kurtosis. We talked about these things, right, already. That's what you want to do. So in the lab on Monday, I want you to play with this, and I'm going to write this down on the website for you to follow along. And you can use charts as well. You can select which kinds of descriptive visual depictions of your frequency analysis you want to look at. And you get all kinds of funky graphs and so forth. So the characteristics of your data, their shape, central tendency, and variability. The shape we talked about last time. Remember those elements? There was kurtosis, there was skewness, and what else was there? Symmetry. Thanks. Okay. Now, what's kurtosis mean again? Yeah.
How flat it is.
Flatness. And what are the 2 words or 3 words that describe kurtosis? Remember? Yeah. Yeah. Leptokurtic, mesokurtic, and the platypus. Can't forget the platypus. That's the easy one. And platykurtic, right? So platypus, flat tail, that's flat. Lepto, I don't know. Lepto means something. It means thin, and meso something in between. Okay, and the skewness is just positive or negative skewness. And remember, it's the tail that we care about with the skewness. So if the tail points towards the positive side, then it's positively skewed. If the tail points towards the negative side, it's negatively skewed. To me, that's confusing. Maybe you guys actually see it more obviously, but to me that always messes with my brain a bit. And with symmetry, we're looking about how centrally organized things are. So central tendency is this thing we'll talk a little bit about today. That's a measurement of how the data is clustered around a certain central point, the degree to which it is done so. And we measure central tendency in 3 ways, through the mean, the median, and the mode. We talked about mode last time a little bit. We talked about modality. Modality was the number of humps in your data if you were to plot a histogram, because the humps tell us are the clusters. Variability is really is the width of the data, so how different the elements are. If all the data was kind of the same, if you're looking at ages of people in this room, you're kind of all the same age. There's not a lot of variability here. We haven't got any retirees coming in to take this class. I haven't got any prodigy 10-year-olds taking this class. Right? You're all kind of like early 20s. So there isn't a lot of variability here. We have ways of measuring variability. We have something called a standard error. We've got variance. We have a standard deviation, all of which we're going to define as the class evolves. So let's go back to central tendency. Central tendency is our attempt to use a single measurement to describe the quality of our data. We want one thing to characterize the nature of the data, and always, 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 everyone always says average, right? The mean. Now, there's a difference between mean and average, even though in common parlance they're kind of the same thing. Do you know the difference? Yeah. Mean technically is if I add up all your ages and divide the total number of people here, that's the mean. The average is actually different ways of measuring central tendency. So be aware of that distinction. I will try to avoid using the word average and only use the word mean, because when I mean mean, I mean mean. When I mean median, I mean median. I mean mode, I mean mode. But the mode is a kind of average. The median is a kind of average. So mode, median, and mean. This is high school stuff, right? So the mode is the number that occurs most often, or the element that occurs most often. Sometimes there's more than one if there are ties. And the median is the thing right in the middle. So if I were to rank all my data, ranking is critical to this process. What occurs right in the middle? Okay. So then the mean, of course, is if I add them all up and divide it by the total. So mode is the score with the highest value, the most popular thing. So here's people in this room. We've got 1, 2, 3, 4, 5, 6, 7, 8 people. Well, 7 people. The most common one is 27. So the mode is 27. Now, if I were to make a graph, a histogram, it looks like that. 27 clearly is the highest point. That's my mode. What's the mode here? Well, it's probably this one here, which is like 0.01, 0.06 or something, right? But they're kind of similar. We would call this multimodal because they're kind of, there's not much difference here. But technically that one is the mode, but there are 3 modes we can argue about. Right? What's the advantage of a mode? Well, we can use it for any measurement level. So if I were to take data on, again, the provinces in which you were born, I got a bunch of people from Ontario, a bunch from Quebec, a bunch from BC. There's a rational mode there. I can say the majority come from Ontario. That makes sense. I can do it for any kind of data, whether it's your ages, whatever it might be. Okay, it's easy to compute. Everyone understands this. No fancy math needed for mode. That's the biggest hump. Done. And it actually reflects an actual value. What does that mean? If I were to take the mean age here, I might get something like 24.6. Whereas probably there's nobody in this room with an actual age of 24.6 because it's an average or mean. So in other words, the number I have chosen to represent your reality actually doesn't represent any one of you. That's a bit of ironic, right? Whereas a mode, automatically it's something that represents somebody. There's always one number there that's, or one thing there that represents reality. So it's useful too when there's more than one estimate of commonality. So it allows us to be multimodal. We can say that, you know, there 27 and 24 are the 2 most popular ages here. We can say that. So it's useful that way too. The disadvantages is it only gives us one aspect of the distribution. So if I say that the mode here is 24, that's where most people are 24 years old, I don't learn about the range, I don't learn about the outliers, I don't learn about the average, or mean rather, right? So it gives me one aspect and nothing else. And it tends to be unstable. What does that mean? Instability means that if I take the mode of your ages here, and I'd go to my 4th year class later this afternoon, I take the mode of their ages there, they will not be the same. Because every sample is going to be quite different. Whereas if I take the mean, they probably are kind of similar, because the outliers will kind of cancel each other out and bring everyone towards a common centrality. So modes tend to be different from sample to sample. Now, look at that last list over here. 10, 10, 11, 11, 12, 12. There are 3 modes there. 10, 11, 12. They're all exactly the same. Right? There's no real mode there. There's no rational way to summarize the most popular one, because they're all equally popular. It makes no sense. So it's possible to have a sample with no rational mode, meaningful rational mode. That's a big disadvantage. The median is the score that divides the distribution into 2 equal halves. It's not necessarily the middle score. It's the one that divides them into 2 equal halves. That's a very important definition. So 50% are below that, and 50% are above that. So here's the same sample as last time. I've ranked your data here: 26, 27, 27, 28, 29, 30, 31. 1, 2, 3, 4, 5, 6, 7. Right? So out of 7 individuals, the middle one's going to be the 4th one, because there'll be 3 below and 3 above. So 1, 2, 3, 4. 28 is our median, because there's an equal number of people below 28 and an equal number of people above 28. Again, high school level stuff, elementary school stuff, but it's amazing how confusing you'll get as the data sets get larger. Now, there's something special about that particular data set. There's an odd number of individuals. So there's an obvious central guy for whom half of the results are to the left and half of the results are to the right. What do I do if there's an even number? Yes? Sort of. I take the... Sorry, yes? I could take both of them depending upon if they're the same number. If they're the same number, then yeah, that makes sense. Let's look at that. Let's look at it. We look at, we want to make sure we need a number for which half are above and half are below. So here I've got 6, 1, 2, 3, or 8 rather, 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4 is 28, 29, 29, 4. So somewhere between 28 and 29 is the midpoint. So halfway between 28 and 29 is 28.5. So there are exactly 4 people below 28.5 and exactly 4 people above 28.5. Is any one person 28.5? No. So once again, my summary statistic here describes everyone but nobody. There's no actual one person who's 28.5. So it's a bit ironic. Unlike the mode where there's always one person with that, at least one person with that number. Okay, so it's our median here is a constructed number that is not in the original data set, but serves as the bifurcation point for which half are above and half are below. Again, elementary level stuff, but it's amazing how many will forget that. Okay, the advantages. The huge, huge, huge advantage of the median is that it's not affected by the outliers. So again, if I've got a bunch of people here, you're all kind of like 20, 21, 22, 23, and if there was like a retiree who's 58 taking this class, or 68 rather, because 58 is still working probably, if I were to take the mean, he would skew your mean way high. But because he's just one number ranked, he doesn't skew it. All I care about is that he's above my median. He's not skewing the numbers. So whenever we have extreme outliers, the median is the better estimate of central tendency. I told a story last week of people complaining that my averages of my students were too high compared to the averages of other, the means rather of other classes. My argument was, well, the mean is not the appropriate measurement, it's the median, because you're going to have a couple of individuals with extremely high marks and they're going to skew everything. When you take the median, they don't count for as much. And in fact, the median mark is comparable to the median mark in other classes. So it's important to choose the correct measurement of central tendency to tell the story that you're trying to tell. So it's a good index of what is typical when the distribution is skewed. So again, skewness is a kind of outlying as well, because we got a bunch over here and fewer over here, but the median is going to give us something over there, kind of in the center. And again, it's easy to compute. Everyone kind of understands intuitively what a median means. Really good for ordinal data because you've got to rank. Median only means something if you can rank stuff. Ordinal data already comes ranked. The disadvantages. It doesn't take the actual values into consideration, only the position of where they are in the rank, and then I convert that position to a number. So again, maybe I care that that 68-year-old guy is in this class, depending on the story I'm trying to tell. That doesn't reflect if I use the median. And it isn't necessarily reflective of an actual person. So the example I gave you, that 28.5, there was nobody in the class who's actually 28.5. So I'm using a summary statistic that doesn't actually represent any true person. I know I'm repeating myself for the sake of clarity. Okay? Cool. Then we move on to the thing everyone understands. That's the mean, also called the arithmetic average. There are different kinds of means. You've probably heard of geometric means and things like that. A geometric mean is when you take the mean of the squares of these things. You take the means of the cubes. You take logarithmic means. You can take all kinds of interesting, fancy means that would make you very upset. That's not what we're talking about in this class. Here we're talking about the arithmetic mean, which is just what you know as the average. But beware of the terminology. In mathematics, it means something specific. So in other words, you just add up all the numbers and you divide by the total. So the same data set as last time. The mean here is 28.3. So let's go back. Remember, our mode was 27, our median was 28, and our mean is 28.3, all of which purport to be a summary of the typicalness of this particular data set. Which is the right one? And what does it mean that they're all kind of different but kind of similar? If I were to tell you that I have a data set for which the mean, the median, and the mode are all the same, what can you conclude about that data set?
There's no outliers.
No outliers? Yes. What else? Probably. It could all be the same number. It could be a data set of all this one number, you know, everyone the same age, or probably normally distributed. It's probably really closely be normally distributed. It's definitely symmetrical. All right. So that's one of the things to look at. If we have an enormous data set, and I can't really visualize it yet, but I can compute very quickly these three measurements of central tendency, I can start immediately to figure out, it's probably distributed this way. That's kind of useful. So that's the mean. Mean's easy. Yeah, everyone knows how to do the mean. The advantages is the mean is the balance point, we like to call it. It's when everything's added up. It's picture a scale and weights. Then really, if I would actually take all of your weights, literally your actual weights, and compute the average and put it on a scale, that would be the point of balancing. It doesn't ignore any information, which means that everyone's score in the set contributes. And it's very stable. Stability means if I go from this class to the next class to the next class, I'm probably going to get very similar means. It's robust. Statisticians love that word robust. Robust means that it is resilient to perturbations in the environment. If I compute the mean in this class and in my other class, they're probably very similar. And as a result, a lot of our inferential statistics are based upon means of things. Disadvantages, really sensitive to outliers. Really sensitive to outliers. So again, if I have that 68-year-old guy in here, the mean of this class jumps up to like 29 or so. And that's not typical of you guys at all. Okay? So give a distorted view of what is typical. We have to always look for outliers to prevent using the mean as an inappropriate measurement of typicalness. And very often it is not an actual data value, much like the median. So again, if I tell you that your average age of this class is 23.6, there is actually nobody here with the age of 23.6, but you all have the age of 23.6. Okay, symbols. So remember the difference between samples and statistics and parameters. Statistics are the measurements in my sample. Parameters are the measurements in the reference population. So in the sample of the statistic, very often we use M as the mean. That's the new way of doing it. The old way, which I like, is the X bar. So it's an X with a bar on top. That's the sample mean, or the statistic. The population mean, or the parameter, is the Greek letter mu. Right. So it's an important distinction, as you'll see later on, as we try to do inferential statistics, because it will be trying to estimate mu from X bar. And very often we will use them interchangeably, but be aware we're doing so with the assumption that X bar represents mu. Okay? So, central tendency in normal distributions. As was noted, in a perfectly normal distribution, the mean and the modium, modium, that's what you do when you have diarrhea, modium. The mean, the median, and the mode should be equal. Now, if you're skewed, the mean pulls things off center, and so very often, if you just show me the mean, median, and mode of a sample, I can automatically visualize the degree of skewness. So if your mean is larger than your median, chances are it's skewed to the positive direction. If the mean is less than median, chances are it's skewed to the negative direction, and so forth. Right, I mentioned variability. Variability is the width or dispersion, or the spreading out of your distribution. So two different distributions with the same mean could actually have different widths. Think of it this way. If I've got two people, a 10-year-old and a 50-year-old, their average age, mean age rather, is 30. And if I've got a 25-year-old and a 35-year-old, their mean age is also 30. But their difference between those two ranges are quite high. So the mean only gives me the centralness, it doesn't give me the width. So these measurements of central tendency tend not to tell me the range, width, dispersion of the distribution, and that can be important. So, yeah, screw that, it's not important. So there are four measurements of variability that we care about in this class. The first is range, and range is the difference between the lowest value and the highest value. The interquartile range, we'll define later on, is once we've divided our data into four segments called quartiles, it's the difference between the quartiles. Standard deviation is the thing that we go to most often as our measurement of standard width, and the variance is derived from the standard deviation. So let's go through them now. The range is the difference between the highest and the lowest value. So here are the weight in pounds of a bunch of people. The range here is 80. Take the highest number, which is 190, subtract the lowest number, 110, you get 80. Simply done. The advantage of the range, well, everyone knows how to subtract. It's not hard to do. You understand the range. I can explain it to you in 3 seconds, I just did, and it communicates information pretty fast and easily. Disadvantages is you only rely on 2 scores, the endpoints. It doesn't matter what happens in between. It doesn't give me a whole lot of other information. And sensitive to outliers. If I had that 68-year-old guy in here, and I computed the range, I'll take the youngest one of you, who's probably 20, and that 68-year-old guy, and I get 48 as your range. Without him, I probably get like 4 years as my range. Right? So very sensitive to outliers. And tends to be unstable. So if I go from this class to the next class, the range will be quite dramatically different. And influenced by sample size. By the way, almost everything is influenced by sample size. It's one of the great magic elements of statistics, and one of the most frustrating elements also, is the fact that the more stuff you have, the more people you have, probably the better estimate you have, but also variations in some of these estimates. Okay? So the more people I have in my sample, the more likely it is I'm going to have outliers or extreme numbers. Interquartile range. Okay, this is a tough one. So a quartile is a way of dividing my data into 4 segments for which there are equal numbers of respondents in each segment. So if I were to rank all my data, there's an equal number in each of 4 categories. These are quartiles. So the lower quartile we call Q1 is a point below which 25% exist. The upper quartile, which is Q3, is a point above which 75% live. Why are there 3 quartiles, even though quartile means 4? Yeah.
Because then you put like the 3 to 5 in, and it makes 4.
Exactly. It's not rocket science, exactly. Good point. So what's my middle quartile going to be? Q2. What do we know the Q2 also as? Has a different name. Yes. It's the median, exactly. Because Q2 is essentially a thing that divides the first 25 and the second 25 from the next 25 and the last 25. Right? So the interquartile range is the difference between Q1 and Q3. Another way to look at it is it's a different kind of, the quartiles are kind of like medians, but where a median divides things in half, quartiles divide things in 4, and the interquartile range is just that middle 75% or so, 50% rather, middle 50% in the center here. Why do I care about that? Why is that? Before I go on the next slide, how useful, why is that useful, do you think? Yeah. Exactly, eliminates outliers really powerfully. Now I can eliminate, the extreme ones easily. Hey, that's extreme, that's extreme one. But this systematically says I'm eliminating the 25% of the lowest guys and 25% of the highest guys, and I'm stuck with the key core guys in the 50% of the center. And every year is always, it's even simple math, this is a thing that troubles a lot of students because they screw it up a lot. So spend some time computing interquartile range. I'll give you examples. Here is a list of data. So here we have, excuse me, Captain America's going to sit over here for a bit. We have 11 individuals. Why I choose 11 and not 10? Because conveniently it's an odd number, so someone halfway is going to be a median just to make life easy for this first time. So the median is going to be, and they're ranked here, there's people's weights, let's say, 102 down to 118. I've ranked them. This is the data X, right? I is the substrate. So the median is a halfway point. Halfway between the median and the first point is Q1. That's 105. Halfway between the median and the last point is number 9. It's 115. So here, Q1 is 105, Q3 is 115. The difference is going to be 10, and that's my interquartile range. Now, there's another way of doing this easily. You take my n is 11, you take n plus 1, be 12, right? And here's a formula. Q2 is always going to median, which is n plus 1 over 2. Q1 was always going to be n plus 1 over 4, and Q3 is always going to be n plus 1 over 3 times n plus 1 over 4. So this, I like this formula. It saves a lot of work if you've got enormous data sets, and it works even if you've got an even number. Otherwise, you've got to do things visually, and it gets very confusing. Right. So in this case, Q1 is the third entry, 105, and Q3 is the ninth entry, 115. IQR is 10. So in this one, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, odd number again. The IQR is going to be 175, but what's 135? Let's see how we got that. Here's our list of data. Our median is, where's the median? It's here. In between the median and the first one, 1, 2, 3, 4, 5. It's this one here. In between here. So the trick to this one here, what's the trick here? Oh, yeah, straightforward. Right. So you fill in the formulas and compute. These are easy examples because they're small data sets. If I give you like 200 data sets, it gets a little more confusing. Rely on the formula. Try it visually first, but rely on the formula. It gives you the midpoints here quite easily. Any questions on IQR? All right. Now, if you have an even number, and here, look at this, we have 2 ones repeated. Let's work it out here. So we have 10 people here now, not 11. The formula says find the median. It's over here. So 10 plus 1 is 11 divided by 4 is 2.75, which is 3/4 of the way between 120 and 130. Okay, remember, this number is the rank. It's not the value, the rank. The rank of 2.75 is over here. It's not 125, it's 3/4 of the way between 120 and 130, and that's going to be 127.5. You see that subtlety? All right? And the same way here, we're going to get the formula for this one is 8 1/4. So between 8 and 9, it's not 8.5, it's a little closer to 8 than it is to 9, and it's actually 172.5. So again, the key part that a lot of students get confused about is the formula gives us the rank, not the value, the rank. You've got to convert the rank to a value. Okay. Okay. You can use stat software as well. Here's one online IQR calculator you can use to test out your data if you like. Why do we have the interquartile range? So it reduces the influence of outliers, as mentioned, quite accurately. It uses more information than the range. With the range, we cared about 2 numbers. Here we've got everybody is in play. We've ranked them all. We've got some Q1s and Q2s. We've got some other people going around. And it's really useful for ordinal measurements. Okay. The more clustering around the center, particularly around the median, the smaller the interquartile range. So very quickly, IQR becomes useful in a lot of studies that rely on median measurements. What kind of studies rely on median measurements? A lot of drug trials rely on median measurements. And IQRs are often computed using something called a box plot. Now, am I doing a box plot in the slide? I don't remember. Here's something that's not quite a box plot, but it shows clustering around the median here. Why is that useful? Any idea why it's useful? And notice, by the way, that mean is not in between the values. The ranks are in between the values, but the values are not. It's a subtle distinction that I'm struggling to communicate well, I realize that. The ranks are straightforward, but the numbers on the ranks are not. What we're doing here is figuring out where the rankings are, but here the actual numbers are skewed. There's more beneath the median than above the median. All right. It'll become clear later on. All right. So, disadvantages. It's obviously not obvious to compute. You've got to mess around with formulas. You've got to visualize things a bit more. It's not well understood. It's not intuitive. Not intuitive to me. Not intuitive to you, I guarantee it. Right? It doesn't take all the values into account. Only the Qs. Only the quartiles. That's all we care about. It takes more values in the range, but not all of them. So those are disadvantages. Now, standard deviation is something you've probably heard of before, and maybe you've touched upon in high school. And this is the most common measurement of variability, and it's an index that conveys how different the values are from the mean. So a deviation in statistics is a difference from the mean. So in regular life, a deviation is any time you step away from the path. You've deviated from the path. In statistics, it's any time you stepped away from the mean. So if the mean age in this class is 23.6 and your age is 24, your deviation is 0.4. Right? So that's how much you have deviated from the mean. It sounds like you're doing something wrong. You haven't, because the mean is actually, constructed. But that's, and the standard deviation is the summary of all the deviations from everybody in the set. What's the average deviation of all of them? So, if we look at the standard deviation, here is the mean of a normal distribution. About 68% of all the people in the set will fall in this range here, 34 on that side, 34 on that side. One step beyond, about almost 90% falls around here. So a fixed percentage of cases lie a certain deviation from the mean. Why did I choose these numbers? Because one standard deviation is exactly 34.1% away, gives me 34.1% cases above. And the fact that this is true for all normal distributions, it gives us a lot of power in the future when doing certain kinds of computations. It's not obvious now. Here's the term percentiles. You write your MCATs or your LSATs, whatever it might be, and I scored in the top is something percentile. That's based on this distribution that I placed over here, which is in this percentile, meaning I'm above all of these people here. Okay? We'll do more of these examples in the future. So I know it's confusing for now, I didn't explain it well, but I will in the future. But to summarize, the important part for now is a deviation is how much each individual varies from the mean, and the standard deviation is really the mean of the deviations. That's what we come down to. Okay. So, which variability index do we use in which cases? Remember, we have our various measurement scales, our nominal scale, which is names or groups, like which province you live in, the ordinal scale, which is rank data, the interval and ratio scale, which is our continuous data, like ages and things like that. So the proper central tendency measurement for nominal data is a mode. Hopefully that's obvious. If I'm asking you what province you're born in, I really can't take a mean of what province you're born in. It doesn't make any sense. I really can't take a median because I can't rank these things. I can take a mode. I can figure out which is the most common province you're born in. So nominal data gives me mode. There is no variability index that I could apply here. I can't figure out the width of the bar graphs that determine which province you live in. So I'm done there. For ordinal data, which is maybe your ranking in the class, right? That's that's ordinal data. So the central tendency that's referred to as median. Why? Because ranks don't tell us how far apart you are. It just tells us whether or not you're above the next guy. You could be hugely above him or a little bit above. And a mean doesn't mean anything there, but a median does. For variability, we can use a range or the IQR, because we can't compute means, so can't do anything else. But for other data, continuous data, we can compute means, and means are preferred, because means we can do all kinds of fancy stats, and we can do standard deviations and variances. Variances we'll do later. Variances are essentially squares of standard deviations. Okay. So that's why most of what we end up doing is this, is working on continuous data, because it's powerful and allows us to use these tools. So why do we use all this stuff? Again, to get a sense of our data, to get a big picture of what's going on, to evaluate the outliers. So very often what we do is we trim down our outliers, and then we compute our means. That's called a trim mean. And we answer descriptive questions like, what's the typical age of this group? That's a descriptive question. If someone asked me, in fact, their colleagues do ask me, how old are your students? I tell them, well, the mean age is 23.6, something like that. But in fact, I should say the median age is 23. Right. Okay, and SPSS, like I mentioned, you're going to go to the frequencies, you're going to click on statistics, you're going to go through and explore all that wonderful stuff. That's what it looks like. Skewness, kurtosis. You've got the mean here. You can look at dispersion for, that's their word for variability, dispersion. You can click on standard deviation. You can measure variance or range or all that stuff. Standard error we'll deal with later. Min and maximum are the same as range. So the range is going to be the max minus the minimum. Percentiles aren't here yet. Percentiles we'll do later. We got good display options. So if I ask a class of 10 students what their weight in pounds is, I get these numbers. When I do this, step one, I rank the numbers. So here's my actual data. I rank it to make sure that it follows in order. Ranking is key. You got to rank first. Right? And we compute the total. The total is 1436. What do I do with that? I compute a mean. Wonderful. What's my mode? The most common result? 102. What's my median? Well, there are 10 results here, so the median is going to be somewhere between the 5th and 6th results. So halfway between these two gives me my median, which is 129.5. How do I find the range? Range is going to be the maximum value minus the minimum value, and that's going to be this number subtract that number. Right, 265, okay. Interquartile range, we use our formulas. So that's on my median over here, 29.5, we already got that computed. My Q1's over there, using the formula. My Q3's over here, using my formula. Subtract them, and I get that. Right? So that's how you deal with the data set using the tools we learned today. So your homework is essentially doing that stuff on 3 examples. Right. The looks on your faces, I can't tell whether you're bored or horrified or what. So any questions? No? All right, cool. So we'll see on, is it Monday? Monday? Wednesday? Friday.